In this example, we have a charged metal sphere with half of a microcoulomb of charge on it. And we're interested in the magnitude of the electric field and the electric potential at a certain distance from that sphere. And then we're going to find the magnitude of the force on an electron at that point and the electric potential energy of that electron. So the key concept to this problem, of course, is that the field outside of a charged metal sphere is identical to having a point charge at the center of that sphere containing the same amount of charge. So we just treat it like a point charge at the center. The only difference is that inside the metal sphere, the electric field would be zero, but we're not even asked about that in this question. First, we compute the magnitude of the electric field. So our charge is half of a microcoulomb, so 0.5 times 10 to the negative 6. And then our separation distance, well, we're pretending all that charge is concentrated at the center, and I can see in the graph, that's a distance of 50 centimeters from the point of interest, x, to the center of the sphere. So that's 0.5 meters squared. And I get my electric field strength rounded to 3 sig figs is 1.80 times 10 to the 4th newtons per coulomb. Next, I want the electric potential at the point of interest. And when I run the numbers on V, I get 8,990 volts. In part C, we're asked for the magnitude of the force on an electron at this point. And I can just get that by using the field that I already computed. It's just QE, and because I put the word magnitude in here, I'm not interested in the direction at all, just the size of this force. So just QE, ignoring the sign of the charge on the electron. It's 1.6 times 10 to the negative 19 coulombs. I'll leave units in this calculation just to illustrate how it works. And the field was 1.80 times 10 to the 4th newtons per coulomb. The coulombs cancel and I get newtons out of this. And it comes out to 2.88 times 10 to the negative 15 newtons. That might seem like a small force, but the electron mass is so small that a huge acceleration will be induced by this force. In part D, I'm asked for the electric potential energy of an electron at this point of interest in both electron-volts and joules. So let's work in electron-volts first. And here's how simple it is. I have an electron sitting at 8,990 volts. I still have to keep the minus sign on the electron, but I have negative, the charge of an electron, and the voltage, 8,990 volts. Again, these are unlike charges, so I should have a negative potential energy. And I just get negative 8,990 electron volts. Then I can multiply by the conversion factor that each electron volt is 1.6 times 10 to the negative 19 joules. And my electron volts are going to cancel. And I get negative 1.44 times 10 to the negative 15 joules. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.